Hello, welcome to this video mini lesson introduction to goodness of fit. Remember, goodness of fit is a chi-square analysis that deals with one variable that has multiple categories. Such as the example we'll be using of fifth graders' choice book genres, where we only have one variable, which is the different genres of books, and then we have one row of data where we will put our counts for each of these genres, so the actual number of students who chose a book of that genre. And goodness of fit analysis is also known as a one-way chi-square. So let's look at our example here. We have fifth graders' choice book genres. And the first thing that we need to know is our total sample, our total number of students that we're considering here. Let's just say for our purposes that we have 70 students, okay? Now we have to, as we mentioned in the previous video mini lesson, we have to compare our expected frequencies to our observed or actual frequencies. So how do we figure out what our expected frequency should be? Well, there are two sorts of situations. The one situation is where we have equivalent probability. So in other words, we don't think that there's any reason to think that humor is going to be chosen any more often than sports, etc., etc., etc. And that particular sort of case, our frequency, our expected frequency is simply our n size, our number divided by our number of categories. So in this case, we have 1, 2, 3, 4, 5, 6, 7 categories. So we take our n size of 70 and divide it by 7. So that means our expected frequency for each of these will be 10. And the expected frequency, when it is included in a contingency table like the one we're creating here, is the expected frequencies are put in parentheses here, okay? So our total, because it's our n size, is going to be 70 over here. So let's say we actually, we talk to fifth graders, we look at their books, we see what genre each of their books falls into, and then we count the number of students whose books fall into each of these categories. So let's just say that we have, I'm just totally making up these numbers here. Okay, how many do we have here? 25, 35, 73, 76, 81. Oh, we already have more books than we have students, so let's change this to that. So that means we have 30, 50, 63, we still have too many, 63, 66, 69, 70, I think that's right, but you get the point here, okay? So then what we would need to do is to conduct an analysis to see if our actual frequencies are statistically different from our expected frequencies. And to do that, we use this handy dandy formula. Of x squared, which simply means chi-square, is equal to the sum of frequencies observed minus frequencies expected square. So those get squared and divided by the expected frequency and then summed up. So FO means frequency observed, or the actual frequency. F sub E is the expected frequency. Now, in the situation we just gave, we had equal probability. So our probability, or our expected frequency for each of the categories was the same. Now, we don't have to do it that way. The other way is to do what's called a priori expected frequencies. And that would be if we had some prior observations or prior research upon which we could establish our expected frequencies, then we would use that instead. Like, for example, perhaps from previous studies we know that sports tend to be chosen 16% of the time. So then you'd have to say 16 times 70, because that's our total number here, et cetera, et cetera. So let's say instead it's 20%. 20% of the time people choose sports, so 20% of 70 is 14. And then we would go on there. Based on the previous research, we would have these a priori understandings of what the expected frequencies should be. And so those would not be all equal to each other. Do you see how they would be actually different from each other? And I totally don't know if my numbers are even equaling up to 70, but it doesn't matter, because the point here is there are two ways to get your frequencies, your expected frequencies, either through equal probability, in which case you use this formula here, we're just dividing your n by your number of categories, your k, or based on a priori assumptions, which will be derived from previous observations or research, okay? But regardless of whether your expected frequencies come from equal probability or a priori assumptions, this same formula is going to be used for determining chi-square. Now, when you get your x-square, when you actually find your chi-square value, you then have to use a a lookup table using degrees of freedom. So your degrees of freedom for the one-way chi-square is simply k minus 1, so your number of categories minus 1, and then you use the lookup table to find your exclusion values. If your actual chi-square exceeds the exclusion value in the lookup table, then you know that you have a statistically significant difference between your expected frequencies and your observed frequencies. In that case, your data would support the alternate hypothesis as opposed to the null hypothesis. So this is your brief introduction to goodness of fit, or chi-square with one variable. Thank you. Have a good day. Oh, and let me know if you have any questions.